In this first of a three-part series, we're going to solve for the dynamic temperature distribution in a rod or an object made of a solid single component material with no internal separation or boundaries between parts of the rod. So schematically, this will look something like this. We're going to have inside of this rod t at position x, comma, time equals 0, some initial distribution. It depends on position, some f of x. As the initial, so this will be t0. Okay. Also, we're going to specify boundary conditions. Let's just use one type of boundary conditions here. This is just a constant temperature boundary conditions. But the process that we go through here applies to both flux conditions or no flux conditions and temperature or no temperature boundary conditions. Temperature equals 0 boundary conditions. So what are the governing equations for heat transfer in a rod? If we consider only thermal conductivity, we can write the following equation. This is Fourier's law, second law for heat conduction. So del partial t with respect to time equals the thermal diffusivity alpha, which is a ratio of the thermal conductivity K divided by the material density and the heat capacity. If we consider a solid, then the Cp is equal to Cv, or it's a very good approximation for that. So it's thermal diffusivity alpha del squared temperature del x squared. This is going to be for time greater than equal to 0 and for x within the range 0 and the length of the object L. So this is one part of the equation. We also have to specify the other parts of this equation for actually to order to solve this problem. One of the conditions is the initial condition. T0 is a function of x, comma, time equals 0 equals some f of x. Other conditions are the boundary conditions. We have the temperature for at position x equals 0 for all time equals T1, and also the temperature at the other boundary, x equals L, for all time equals T2. This set of equations here constitutes the actual partial differential equation description for heat conduction through this rod. The first step in the process is to essentially non-dimensionalize the system to make it amenable to analysis and also to give us homogeneous boundary conditions, or temperature equals 0, or the equivalent, the scale temperature equals 0 at the left and right boundaries. These problems are significantly more straightforward to solve if they have homogeneous conditions, and so a little bit of work in the front makes everything else easier in the future. So let's begin this process. I think the best way to begin a process of defining the dimensionless groups of a problem is to write down the equation, first the differential equation here, alpha del squared t by del x squared, and make a list of the units that are associated with each variable. So temperature is one of the 4 fundamental dimensions we use in engineering. Temperature. T is also a fundamental dimension, and it has units time. Alpha equals question mark. X is spatial position, and its fundamental dimension is length. What is alpha? Well, if you don't know alpha a priori, for the problem to be consistent, you can determine it from the dimensions of the other variables in the problem. So here we're going to have temperature by time equals the units of alpha times temperature by the units of the length of the system squared. So in order to figure out what the units of alpha are, you just rearrange this equation algebraically, and you find that alpha, the units of alpha, must have units of length squared over time. This is very important when we want to dimensionalize the problem to make sure that in the end, when we choose our dimensionless groups, everything is consistent. So what do we need to non-dimensionalize the system? Well, let's non-dimensionalize the time and position and temperature. So in the end, we have a dimensionless system that does not depend on the specific units of the components in the system, and also simplifies the solution. So let's find time. What would be a good dimensionless unit for time? Well, let me just write down what I think would be a good variable that captures the behavior of the system and has the right units. And this is the parameter, the length squared of the system by the thermal diffusivity, alpha. I'm going to define this as my time scaling constant. So if we look at this, length squared, this is the length of the actual system, and then alpha has units length squared over time, so the length of the system squared divided by alpha gives us, in the end, units of time. So this we can call our first parameter. Let's call this parameter, what did I choose in my notes here? I just developed the dimensionless time, tau, equals alpha by L squared times actual time t. So this now is dimensionless time, and you can figure out your real time by just inverting this equation and going either direction. Okay, so this is the first step in this problem. We found a good scaling for time. Now what about position? Well, I think it's a natural choice for position as the length of the system, and that is very oftentimes a natural choice. So here we're going to have alpha. X is on the interval 0 to L. What we want to do is map this to a new independent variable, psi, which is on the interval 0 to 1. And how we do this? We just divide through the whole thing by L. So then psi is defined as x divided by L. And this becomes our second dimensionless parameter for this system. Now we need the last one for temperature. Now there are a number of appropriate choices for temperature, but one of them makes the problem significantly easier to solve, and that is the following. If we define our temperature dimensionless parameter theta, the one that makes the most sense, I'll tell you in a minute why, it's because of boundary conditions, equals T1 minus T divided by T1 minus T0. And what is T0? T0 is our initial conditions. So let's just, for the simplicity of this problem, specify this as a constant, and we can later relax that condition. Why is this a nice system of dimensionless units? Well, if you look at this and substitute this into the boundary conditions, what you'll see is that theta at x equals 0, comma, all time greater than 0, equals T1 minus your initial temperature boundary condition at that point, x equals 0, comma, t greater than 0, divided by T1 minus T0. What does this equal? This equals 0. The same thing can be true shown for the right-hand side. Now x equals L, or in the future we'll show this as psi equals 1, comma, time greater than 0 equals 0. So let's substitute in all of our scaling parameters and see what the resulting equation is. So we're going to start with our equation, del temperature del time equals alpha del squared temperature del x squared. First, we have time going to be equal to L squared by alpha times tau. I just flipped around the equation we had earlier where we defined tau as our dimensionless time. Substitute that in here. Now x is going to be equal to psi times L. Substitute this one in here. And we'll substitute in our theta equals t1 minus t at position x, comma t greater than 0 divided by t1 minus t0 in for our temperature. In the end, after you do this substitution, let's do the first ones together, and then you can do theta on your own. Because it's a little bit more work, and I don't want to bore you to death on this video more than this problem already requires. So, if we substitute in our time here, we have over partial L squared over alpha times tau equals alpha del squared temperature del x, which is going to be equal to psi times L squared. So let's move this out, multiply through. We're going to end up with alpha by L squared del t equals alpha by L squared del squared temperature del psi squared. This is a tau now, not a t. Let me be careful about that. What we have is that these terms cancel out, and the first run before substituting in theta, you get del temperature del tau equals del squared temperature del psi squared. And then the boundary conditions that go along with this are similarly convenient. Now I'm going to put dot 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 here to show what happens after you substitute in with your theta. Del theta del tau equals del squared theta del psi squared. Theta psi comma 0 equals 1 for the initial conditions. Theta psi, let's put 0 here, and tau equals 0. Theta at 1 comma tau equals 0. So that's the first bit of work you have to do ahead of time before you can actually solve the equation. The equation we're going to solve in the next two videos is going to be this system of equations right here.